Hello and welcome to day 6 of Unit 4. We're going to start things off today with a warm-up. So go ahead and take a look. If x squared plus xy equals 10, when x equals 2, what is dy dx? Okay, so the first thing that we have to do is notice that for looking for dy dx, we're going to have to take a derivative. Okay. So let's see, the derivative of this with respect to x is 2x plus first times the derivative of the second plus the second times the derivative of the first equals 0. This is what I'm solving for. So I need to have an x and a y to plug in, but they only gave me an x. Well, I have a function up here, right, that I could plug 2 into. Okay. And get that 4 plus 2y is equal to 10. So y is 3 when x is 2. And if that's the case, 4 and 3 is 7. Subtract from the other side, divide by 2. Y prime must be negative 7 over 2. And it was a multiple choice question, but I made it a free response just by taking out the choices. All right, to get started, we have a little bit of vocabulary that we need to talk about. Rectilinear motion versus distance versus displacement, velocity versus speed, speeding up versus slowing down. First thing, rectilinear motion, what is it? Rectilinear motion is any motion along a single axis. Now this can be along a horizontal line, a vertical line, a line at an angle, whatever it is, it's one-dimensional motion along a line. Okay? So that could be a line like this with a particle that sort of goes back and forth like that. It can be a horizontal line with a particle that goes up and back and up and back, whatever. But it's one-dimensional motion along a straight line. Distance versus displacement. Distance is adding up all the increments of motion, neglecting moving in the opposite direction. So this would be like the total ground covered. Okay. Whereas displacement is the difference in your position from start and end. So it's end minus start. And again, that's displacement. And this is distance. Let's see, velocity versus speed. That one I think we should be familiar with. Speed is the absolute value of velocity. Velocity has magnitude and direction. Speed only has magnitude, doesn't have direction. Now, speeding up versus slowing down, this is the one that's going to be new. So there's two scenarios. Well, three really. But they're speeding up and slowing down. So the only way something could be speeding up is if the velocity and the acceleration are in the same direction. Slowing down, velocity and acceleration are in opposite directions. Okay, so think about it as if I said my velocity was this way, whatever the magnitude is, it's that way, and I'm speeding up, or excuse me, I'm accelerating that way, then I'm speeding up in that direction because I'm accelerating in the same direction as my current velocity. Okay? Now, if my velocity were that direction, however, my acceleration was this way, in other words, I'm decelerating, then I'm moving in that direction with some velocity, however, there's some force, acceleration, pulling me back this way. So I would be not speeding up in that direction, but slowing down in that direction, eventually stopping and coming back the other way, because acceleration has pulled me back the other way. Okay? So slowing down, velocity, acceleration, different. Speeding up, velocity, acceleration, the same. All right, so for this first example, we're going to look at a graphic representation of a particle's position. Okay? Let's say this particle is moving horizontally along a line. So if its velocity is positive or going to the right, okay, that's positive, negative. That just seems natural. So the first question about this graph is what is the position at time t equals 0? It's 0. Sweet. Okay. At time t equals 1, is the particle moving left or right? Well, at 1, the velocity represented by the derivative of position, which is the sort of tangent instantaneous rate of change there, is negative. Okay? So at time t equals 1, s prime of 1 is negative. Therefore, moving left. Okay. At time t equals 1, is the particle accelerating or decelerating? Well, acceleration, right, is something to do with the second derivative of position. And the second derivative talks about concavity. Okay? And here, it's pretty evident that at that point, the graph has this concave down shape. So, a of 1, the acceleration at 1, or the second derivative of s, is negative because I can see that the curve is concave down. Okay, and therefore we are decelerating. Now, putting those two things together in what we talked about briefly in the vocabulary, at 1, time t equals 1, the particle is moving to the left and decelerating. The velocity is negative, the acceleration is negative, they have the same sign, so I'm moving in this direction, and my acceleration is in that direction. So I'm speeding up. So at time t equals 1, the particle is speeding up because velocity at 1 is negative, and the acceleration at 1 is negative. Now that might sound counterintuitive, right? These things are both negative, but I'm speeding up. That's okay. I can be speeding up in the left direction. I can be speeding up in the negative direction. I can, you know, when you drop a ball from a distance, it has a negative acceleration, and its velocity is down, and therefore it's speeding up, right? What about t equals 2? Oh, t equals 2. Well, at t equals 2, okay, the velocity at 2 is still negative. However, the acceleration, I've slipped into this sort of concave up shape. So the acceleration at 2 is positive. So I'm still moving left. However, this acceleration force is now pulling me back the other direction. It's not pushing me in the same direction I'm moving. It's pulling me in the opposite direction. So I'm slowing down. Okay. All right, so now we're going to take that same graphical example and we're going to attach a function to it. Okay, this graph is actually the graph of this function, t cubed minus 5t squared plus 4t, and we're going to do an algebraic representation of sort of the same thing that we just did by looking at the graph. Now we are going to keep the graph here so that we can sort of check our answers as we go. Remember, this is just an introduction to the lesson, but be prepared to answer these kinds of questions without the graph or without a graphing utility. Now, the numbers for this problem are going to require a calculator because there are some odd, strange decimals and some things that don't factor quite right. But be prepared to do problems that do factor nicely, that do have nice, neat numbers, and that you would have to do without being able to see the graph. Okay. All right, so find the velocity and acceleration function. That's easy enough. That's just like taking the first and second derivative. So the velocity is just the first derivative of position, which in this case is 3t squared minus 10t plus 4. The acceleration function, which is the derivative of velocity, or the second derivative of position, is just 6t minus 10. Okay, not too bad. Find the position, velocity, acceleration, and speed at t equals 3. The position uses the original function. So S of 3 is going to be 3 cubed minus 5 times 3 squared plus 4t, which is negative 6. I wasn't given units to work with, so I'm just going to label mine units. All right, position, the velocity, plugging in 3 here. It's 3 times 3 squared minus 10 times 3 plus 4. Oops. I just saw that was a mistake there. Okay. And this comes out to be something like 1. Yes. And that's 1 unit per, we'll call them seconds. This is a quickly moving particle. So 8 units per second squared. Okay? And the speed is just the absolute value of velocity. In this case, the speed and the velocity have the same value. Now, obviously, they always have the same magnitude, but velocity is in the positive direction, and speed's always positive. So we can add that up here. Typically represents speed as the absolute value of velocity. So if we wanted the speed at 3, it would be that. Okay. Now, when is the particle stopped? When something's not moving, it has 0 velocity. Right? So that's what we want to say here. We want to let velocity equal 0. We want to let the velocity equal 0. Okay, which is 3t cubed minus 10t plus 4. And when that's equal to 0, we're going to have to end up doing a quadratic formula. So we get negative b plus or minus square root of b squared minus 4ac, I think it's 52. Well, the whole thing here comes out to be 52. Divided by 2a, which is 6. And this reduces to 5 plus or minus the square root of 13 over 3. Not bad. Okay. And then our two values of t, when plugged into the calculator, are 0.495. Let me double check. 465. And 2.869. All right. So at these values of t, my particle has 0 velocity. Now, graphically, what I've found here are these points. .465, and here, which is 2.869. Obviously, my scale when I did this graph is a little bit off, but that's okay. You get the idea. All right, so those are the points that we found. I'm going to keep this consistent and do a line like I did on the other. Okay, now, the big question is, when is the particle speeding up and when is the particle slowing down? Well, we can look at the velocity on a number line. I had two critical points, 0.465 and 2.869. And of course we could plug in some values, but we're going to look at the graph and see that here the velocity is positive. So positive. Here the velocity is negative, 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 negative. And then elsewhere, it's positive. Okay, now, acceleration. I need to find this point of inflection, because that's going to tell me where the concavity changes from concave down to concave up. And that's where my acceleration changes from being negative to positive. So I know that my concavity is negative here, and then it's positive. So I know at least that, but I got to figure out that point. And to do that, I just set acceleration equal to 0. And if you do, you can see that t is going to be equal to, what is it, 10 over 6, or 5/3. Or 1.667. Okay. Now, to finish things off, now we can see I have distinct areas of where I'm speeding up and slowing down. Here I'm slowing down because velocity and acceleration have different signs. Here I'm speeding up because velocity and acceleration have the same sign. Here I'm slowing down because velocity and acceleration have different signs. And then at the end, my particle is speeding up because velocity and acceleration have the same sign. So I am speeding from 0.465 to 1.667 union 2.8 or 2.869 to infinity. And then I'm slowing from -0, because time can't be negative, from 0 to 0.465 union 1.667 to 2.869. Okay? Slowing down, speeding up, slowing down, speeding up. Okay, so for the last example, we're going to look at distance versus displacement. And again, different example, but we're still using the same problem. So I've sort of kept all of this stuff over here so that we can refer back to it, because these points are going to come into play. Okay. What is the total distance traveled on the interval from 0 to 5? Okay. Well, remember, distance traveled is the total distance that I've covered, the total ground covered. So if I walk to the left, or I walk to the right, and then I walk back to the left, that total distance that I've traveled or that I've walked, I have to accumulate. So I need to take into account when the velocity changes. Right? I need to take into account that here I'm gaining ground, and that from here to here I'm losing ground, but I don't want to subtract that. I want to add it. Okay? So in order to do that, we're going to take the absolute value of the difference of all of these little intervals here. Okay? So we'll go with the absolute value of the position at 0.465 minus the position at 0. That gives me this distance traveled. Okay? Or this distance traveled. Because distance is represented on my vertical axis. So that distance traveled. Then we're going to add that. We're going to add to that the distance from here down to here. Okay. So we're going to do the absolute value of S of the 2.869 minus S of 0.465. And then we're going to add to that the distance from here up to wherever 5 happens to be, which is going to be quite high. Okay, so that'll be S of 5 minus S of 2.869. Okay, this is something that I would require a calculator for you to do, unless the numbers were nice and neat. In this case, they're not, and this all works out to be a nice number of 33.88 units. Okay. What about the displacement? Well, displacement, first of all, can be negative, right? If I start at 0, and I go over there, and then I go over here, and I go over there, and I go over here, and then I end up right here at -1, my displacement is -1. Okay? So my displacement is just the end minus the start. And in this case, it's 20. And it's 20 in the positive direction. So I started here, I went that way a little, I came back, and then I shot back that way, and I ended up 20 units from where I started. Okay? So distance versus displacement.